So
All right.
early on in our research, many, many years ago, I came and I was thinking about melodies. This might have even before we started the Menta. I came to this realization that the brain has this really big problem it has to solve over and over again. It has to be able to represent things that are commonly observed in the world, and it has to be able to represent them uniquely in different contexts. So you had to have two different representations. You had to have one representation, which was the thing you're observing, and another is an equivalent representation, but it's unique. And they had to be tied together. So you think about in a melody, the notes are coming in or the intervals are coming in, and they repeat, over and over again, different notes. It's like at different points in the melody, but you have to have a unique representation at each point in the melody. And this is a general thing that applies to sensory motor as well. So this was a big problem, and this was the genesis of the sequence memory. So the basic idea was, it was suggested by anatomy and physiology, was that if you take a layer of cells, and this is going to be, by the way, this is going to be a neuroscience presentation. So again, you have to interpret this, how we're going to do this in mind. Mini columns represent the features, and they do so in a non-unique way. Meaning that they're just like the input comes into the brain from a sensor, ears or whatever, and it forms a representation of what it's sensing, and that representation is the set of mini columns. And if I sense the same thing again, the same mini columns will become active. So these particular features can appear on multiple objects in multiple locations on an object. So it could be edges, like the visual edges we see in V1. They can appear at different locations on an object, they can different objects. They can also be intervals in the melody. And if you look at the biology, it suggests that a column of cells can only represent a limited number of these features. So if we look at, like in V1, you might see there's oriented edges, we might call point normals, or edges of an object in some sense. And they go through maybe every 10 degrees. So there's maybe 18 or 9, depending how you look at it, or excuse me, 36 or 18. And then you'll see like some of these mini columns will be active, and it's because they're clustered. So like here I show 4 of these little mini columns active because several of them will be active around a particular orientation. So if you think of this like a line orientation, there might be 1 or 3 or 4 mini columns that are active to lesser or more degree, depending on where they are. And so there's a general belief there's a sort of a Mexican hat inhibition between mini columns. And so if you look at this as a 2-dimensional sheet of tissue, I'm only showing a picture of 1 dimension, you would have a little bump of activity that's sort of centered around the current feature, and the adjacent mini columns would be related, slightly different features. And that as you observe things, this bump would appear in different locations on the sheet of tissue. You have to have multiple bumps if this is going to work. And I'll come back to it in a moment. So I show this picture showing like these 4 little mini columns active. What it would be, there'd be lots of mini columns, and there'd be actually multiple bumps of activity, but all the bumps would be representing the same thing. It's sort of redundancy in some sense. See, sort of. It's a lot to say. I didn't draw a picture of this in 3D.
Just to clarify, sorry, multiple bumps in each kind of hypercolumn, like each column?
Yeah, right. I'm gonna skip right ahead to the just show you this next slide here. Remember, this is from the Tank paper about mini columns, about grid cells. And if we recall, we've discussed this picture before. This shows 1 grid cell module. And in that grid cell module, there are 6 repetitive units. 6 units are basically sort of mini grid cell modules. So each of these 6 units is sort of a complete tiling of the space. And so in this case, what they observed, they observed there'd be 6 bumps of activity in this grid cell module. So there'd be 1 in each of these 6 quadrants here. And they kind of all represent the same thing. And as a bump moves, like in this case, these are grid cells. So if the location change, a bump might come off to the right of this object, of this column, and more bumps would appear on the left. So you have to have multiple to make the system work. You can't just have 1 bump of activity, because that bump of activity could be on the edge, and there's not enough cells involved. So this picture here is a grid cell module, but I think the exact same thing is going on in columns in the cortex. both in layer 6 and layer 4, that you end up with multiple bumps of activity because you have to have it for the numbers to work. And you also have to have it because at the edge of these columns, you have bumps of activity disappear, and you have to have other ones reappearing on the other side. So what I'm referring to, I realize there's a lot at once here. So what I'm showing in a picture of in the previous slide, I'm showing just one of these little areas here, equivalent, and I'm only showing as a 1D picture. I'm showing there's like a bump of activity in a 1D set of grids of mini columns. But in reality, this picture here of grid cell modules is very equivalent to what I think is going on in the cortex, where you have many, some sense, every one of these cells is a mini column. There's more than they're shown here, and there's multiple sets that are doing the same thing. Is that,
and so in visual cortex, in visual cortex, I guess, yeah, as you move through the column, kind of along the parallel to the surface of the cortex, you get the gradual change in the orientation.
Right.
And so
but you'd have,
but then you would have like, let's say this is the preferred orientation here. Eventually you have a repetition of that over here.
What, I'm not seeing anything you're drawing. What are you drawing?
Oh, I'm using my hands.
Oh, sorry.
So this is the column. You have the preferred orientation here, and then as you move along the surface. Oh, do you want me to?
I lost my Zoom screen here. Where the hell is it? I no longer see anything about Zoom.
If you stop there,
I got it.
I don't know if that's going to cause problems.
Okay. There we go.
Okay, you see me?
Yep.
Yeah. So if this is the column, and so you have a preferred orientation here, and as you move along the surface, that kind of gradually shifts, and eventually repeats.
Right.
And so what you're saying is, yeah, firstly, obviously, because this orientation is similar to this one, and this orientation is similar to that one, that's the kind of Mexican hat in a certain area, multiple columns. But then later on in a column, the other hat is where that same orientation appears again, assuming the only input was this bar kind of thing.
Right. And that's general. I didn't make that up. That's a lot of people have speculated that's how it works, and but no one's really sort of articulated in the way we talk about it. But the idea that there's a Mexican hat inhibition between the mini columns, that explains why they're bunched together like that. It would also explain how many different representations a column can represent, because it's within that spectrum of a Mexican hat inhibition before you get the next bump. So those things all kind of play together. But I think you've got it right. So you can imagine looking down the surface here of a cortical column, just like that picture I was showing of the grid cell, and you'd have several bumps of activity all kind of representing the same thing. And a new input, you'd have another set of bumps in different locations, but they're also representing the same thing. Anybody else have further questions?
Yeah.
Oh.
Is it that all the bumps together create a unique representation for that edge, or can we just have one?
We'll get there in a moment. Okay.
Okay.
But yeah, I guess the TLDR would be the sparsity in the mini column will be critical for that.
Right. So,
but,
are you seeing my picture again now?
Yeah, your slide 1.
Yeah.
Now it's black. Okay, now we're good. All right.
Okay. And then what? It's funny because I switch and now it changes my sound. All of a sudden, my sound's like a computer again. What the? I don't know why it's doing that. All right. Well, you guys can hear me still. I don't know why it's doing that.
Yeah, we can hear you.
Now it's coming back in. It's like it's randomly switching my speaker in and out. Okay. So, all right. So, do we have an understanding of this? Or more questions about this?
Yeah, just a quick question. It was still on the shape of the bumps. So, just as a sanity check, from a lot of Numentis' previous work and publications and stuff, didn't necessarily have this bump, right? I mean, it may have been, the idea was there, but they would have been kind of, one feature was like a random selection of mini columns, and another feature was another random selection.
Right. We were testing out the mechanism, which I'm about to describe, and we weren't really applying it in any particular instance, and so.
Okay, yeah. I just wanted to check understanding and
Right,
memory wasn't wrong. Okay.
right. You know, if I could go back with a magic wand, I could make all the things we presented in the past equal to what we have today, but you know, it's not. Right. So we didn't talk about that. In fact, we tested the system sometimes with you know, you could have thousands of objects or thousands of features or you know thousands of mini columns. Each one could be a sort of a random distribution of mini columns. It wasn't like this with the bumps and all this kind of stuff.
Okay. Thanks.
So right. All right. So this is how you basically represent a feature in a non-unique way. And going back to your question, Jose, the different bumps do not add any new representational capacity. At this point, they just add some redundancy. But the next thing is going to make a big difference. The next thing is that the key insight was that if you assume that not all the cells in this mini column, which again we're talking about one layer of cells, so I'm labeling this layer 4 here. There may be anywhere you can take your guess anywhere, say between 10 and 20 neurons in a mini column in that layer. If you just activate only one of those cells, like the blue dots here, and not all 10 of them or all 20 of them, whatever the number you pick, then you're able to create a unique representation of that feature. So you're still activating the same mini columns, but by picking one of 10 cells or one of 20 cells, you get this very, very high representational content. So imagine you had 6 bumps of activity. Each one had, let's say, 5 active mini columns. You pick 1 out of 10. So that's 10 to the 30th is the number of things you can represent by selecting one of these cells in each mini column. And we worked through a lot of the math about this. You could pick them randomly and it would still all work and they wouldn't interfere and all that kind of stuff. But this was the basic idea, is if you picked 1 cell per mini column, you'd end up this is a unique representation of the same thing. So these 2 representations would be sort of co-located in the cortex. At the columnar level, the mini column level, or at the cellular level would be 2 different representations of the same thing. And so you could have many different ways of representing this feature in different contexts in the world. And each one of those would be very unique. So that was the basic idea. And we did a lot of work to make sure the numbers worked out, and they did. It seemed like the brain sort of picked just the right set of things to make it all work.
So just to make it concrete, by representing the same thing, let's say you can select different cells within a mini column.
In the active mini columns.
In the active mini column, and let's say that represents color red. It will still be, even if the different cells are activated, it'd still be color red. It's just that.
Well, if you looked at it in the red's not a great example. We could use it.
Okay.
If you looked at it, it said, okay, let's think of it as an edge of an object. Okay, can we do that first? There's an edge of an object. So it's the active mini column just represents some sort of edge at 30 degrees.
Okay.
Well, that edge could be on different places on the same object, the 30-degree edge. You could be on many other objects. In fact, there's only maybe a dozen different edge orientations you can observe. So it's going to be one of those dozen. But what you want is that representation that is unique for a particular object on a particular location and unique in all the objects in all the locations. So this is very much what we see in border ownership cells. This is exactly what border ownership cells are. They look at that one of those blue dots and they say, hey, this cell is always active at the tail end of the tiger, at this location on a tiger. How could that cell only, in V1 be active on this location on the tail of a tiger? It's because it's a unique location on a unique object. And now these cells, even the blue dots, are not unique themselves, right? They're more unique than the mini columns. But it's a combination that's unique, right? It's really the combination that's unique. But in the case of border ownership cells, one of these blue dots would always appear on this particular point on the tiger, and it wouldn't appear most other places. But it would appear occasionally other places too.
Okay.
Does that make sense?
Yeah. So even if we have selected different cells, it will still represent the 30-degree edge It's just that it will be active in a different context or different location.
Right.
Okay.
So the gray dots are your common feature edge.
Yeah.
And the blue dots are the unique representation of that feature.
Okay.
And for what it's worth, yeah. And that fits really well with kind of neurophysiology studies like the Hubble and Weasel experiments. I can't remember if you've kind of come across those, Jose, but when they kind of looked at like orientation preference in cats and stuff like that, where if you penetrate the probe down perpendicular to the surface of the cortex, all of those neurons just seem to respond to the same orientation, which seemed really weird at the time because it was kind of like, well, that's sort of a waste of information. And then if you go kind of perpendicular, you get that gradual shift in sort of preference of orientation.
Right. I always thought that was a very weird thing too, Niels. I looked at that and go, that can't be right. The brain, why would the brain make all these cells do the same thing? And the pat answer people sometimes gave was like, oh, well, they're all just, it's redundancy. It's that kind of thing. I said, that doesn't make sense. And of course, what other things happen when to get all those cells in the minicon to respond, the blue dots to respond, they have to give them like sinusoidal gratings, which are non-objects. Those are things that you don't really, there's nothing unique about them. But they notice that when the animal would observe a realistic image, that the classic receptive fields, which were defined by looking at sinusoidal gratings, those classic receptive fields went out the window. Cells didn't respond as they expected them to. So they said, oh, this blue cell responds to an edge at 30 degrees, because we proved that with the sinusoidal grating, but then they show the animal real world images, and that cell often doesn't respond at all when it's got a 30-degree edge. And they're like, what the hell's going on? That kind of thing. This explains all that. Okay. By the way, it doesn't even have to be one cell per mini column. It could be 2 out of 20. So there's nothing magic about that one. It just has to be sparse type of thing.
Right. So this allows us to like represent 30-degree edge in many, many, many different contexts and
yes, like gazillions of contexts.
Yeah.
So it doesn't mean you can remember them all, but the representational capacity is there.
Okay.
It's very large. We need that. Yeah. If you think about like if this is an interval in a melody, well, there are thousands of melodies and each have many, many notes, and a particular interval appears many, many times in many different places in different contexts. I need to be able to represent. Maybe there's only 12 or let's say 25 intervals or 12 notes, whatever you want to call it. There's a limited number of things that go in a melody. Yet you have to, each time a new note comes in, you have to have a unique representation for that input at that location in that melody. So that was the genesis for this idea. So then to make a sequence memory or a model of sequences, it's pretty simple. You just have to associate the active neurons at one moment in time with the active neurons at another moment in time. So I'm not showing that here. I'm just showing the one set of active neurons. But imagine if you go through a sequence, you would have a series of these activations, these blue cells and the mini columns, and each time each note or each element in the sequence would be different. And then if you just associate, one pattern to the next through horizontal connections, you would learn to associate a pattern A with pattern B, and then pattern B with pattern C, and then pattern C with pattern D, and so on in a high order sequence.
When we talk about the layer 1 input for the specific timing between elements in the sequence, are you thinking of that as being like an additional conditioning? Like basically
yes.
The current element predicts the next element, but that only works if the correct timing signal also comes in layer 1?
Right. I was thinking of showing that in this figure, and I said, oh, it's so complicated. I didn't have time to do it. And then I said, oh, I bet you Vivian or someone's going to ask me about it. My prediction was correct. Yeah, I'm not showing that here. What I'm showing here is it shows the transition from node A to node B, or element A to element B to element C and element D and so on. But as in melodies and often in other things, there's usually timing between those. And so you don't want to just run through these sequences as fast as you can. You need some way of gating the transition between one element and the next. So that would be the layer 1 input, which I'm not showing here. And of course, it's complicated. I won't get into the complication. But anyway, the idea basically would be that when you're at an element in the sequence, it predicts the next element, but you also want to know when it's going to occur. And so the next set of cells would be depolarized, but you wouldn't really expect the note to come in until the correct timing signal was presented on the apical dendrite. So I didn't show that here because we were just talking about locations. Is there questions about that?
Yeah. And then just to double check that we're not misunderstanding on the how location in the sequence or element in the sequence can be represented. So you say ordinal location cannot be decoded, but the SDR is unique to that element in the sequence, right? So we know where in the sequence we are, but there isn't like a common representation for the first element in the sequence for all of the sequences.
It is decodable. Right.
Yeah.
If I had my magic wand, I could look at the SDR, that is the activation of these cells, and I could say, oh, that is the 23rd note in Beethoven's Fifth Symphony.
Yeah.
But I can't. I'd have to have a magic wand, or I'd have to have learned an association with that, which we're going to see in a second.
Yeah.
So
it's kind of like how the locations are unique to the object as well. Like a specific location representation doesn't necessarily translate to other objects because it's like a unique location to that object.
Right. There's no such thing as a zero location.
Right. That was like another big thing. There's no sense of zero location in sequence. There's no sense of origin in our in the grid cells. Right. So it is true that, so this is where Vivian and I got a little confusion here, because this is encoding the location on the object, but it's not like anyone reads it. You can't read it out, and you can't say, let's go to the fourth location. You can't do that. You can just say, I have an SDR, and you and I know that it's the third location and it predicts the fourth one, but I can't say, look, what's at the sixth location in the sequence. You just can't go there.
But two columns could vote on it. Like they could form associations between their specific unique SDRs at that point in time.
But right. Well, I don't think they would, but you could, but that still wouldn't tell you the location. I'm just saying there's no way of reading out like this is the nth element in the sequence. You can't read it in the SDR. You can associate. If I had a separate column that was just keeping track of ordinal numbers, then yes, I could associate with that ordinal number.
Yeah, I agree with that there isn't like a 1, 2, 3, 4, 5 representation anywhere, but why would you not think that they could vote on us?
Well, you said another column. In my next reveal here, the SDR is voting on location. So can we just jump ahead to that? Right. Yeah. Can we just Right. So this is the basic mechanism we had for the model of sequences. And we tested this a lot just to make sure it worked and the numbers worked out and so on. We didn't do anything realistic with it. So then when it comes to modeling objects, sensory motor learning, it's the exact same thing, but we're using the same cells, in fact. Let's say layer 4 here. So we have this feature, we form a unique representation of it. So we have the non-unique representation at the mini columns, feature not unique, then we feature unique to object location. So in the previous one, the model of sequences, you can just, as long as A follows B and then B follows, C follows B and so on, you can learn that up here in a high order sequence. But now we want to do sensory motor learning. The order in which the patterns appear are not a high order sequence, and therefore in layer 4 itself, it cannot predict what's the next input on. It doesn't know that. So our basic model for modeling objects, which we're all familiar with, is you have a second layer of cells that represent the location, and we're pairing the location with the pattern in layer 4. And so in this second layer of cells labeled 6A, we're representing location. And this is how I viewed it, and I've just walked through it. I've always felt like the grid cells themselves are not unique. Remember, they're they do not represent a unique location object. They're like one of 15 or 16 possible locations, and they repeat over and over again. That's very much like the orientation columns in layer 4. Very similar to that. It's a non-unique representation of location. And so I've always viewed it this way, that the mini columns down in lower layers, some of them are going to represent the grid cells themselves. And then if you had a separate set of cells underneath them, the blue dots, so then you could make a location that's unique to both the object and the location on the object. So I say this is speculated because this is not generally observed. And I'll come back to that in a moment. But this is what's required theoretically to make this whole system work. You basically have to say, okay, I have a non-unique location, which is grid cells. Those are updated by movement. And then I'm going to pick a unique version of each one of those things in the same bumpy way as we did in the bump of activity, which is what we see in grid cells. And so now I can pair the unique location with the unique feature up above. And since the blue dots in the layer 4 and layer 6A are both unique to the object and to the location on the object. They are both, just one is updated by sensory input and one is updated by movement of the sensor. But they're equivalent. I mean, in some sense, they both are unique to the location and the object. And therefore, if you know one, you can predict the other, and if you know the other, you can predict the previous one. So this is the genesis of our basic idea about how sensory motor modeling works. I've convinced myself, and maybe correctly or incorrectly, that you have to have this unique location to make this whole system work. It wouldn't be sufficient just to use grid cells, which are not unique. You have to have another representation which is unique. And if you assume that that's the case, then you can imagine a parallel construction between the upper layers and the lower layers, just like this. And now this will work. And so inference is a matter of sensing and moving and sensing and moving. You're updating both of these two things simultaneously. And as you go, you narrow down the choices, that things that are available that match both the sensors and the movements of the sensors. So this is, yes, go ahead.
And how does the different anchoring of the grid cells play into that? Like does that create an extra amount of unique representations?
It only does if you have multiple grid cell modules, right? Well, yeah. So at one point we said, oh, the way we're going to get this unique location is to use multiple grid cell modules. And that's in our paper, the first paper we wrote about this, that's what we assumed. But it never really worked. There weren't enough grid cell modules, first of all, and it didn't look like you could access all of them. And they had different scales, substantially different scales, which was also a problem. So we kept looking for more grid cell modules, like they could exist in more places. And that would solve this problem too. You could have multiple grid cell modules in a column, and each one would anchor differently. So that was one idea. It never really worked out because there weren't enough, there wasn't enough cells, there weren't enough grid cell modules to do that. But that's how we started. This is an alternate flavor. This says there's another way to get to a unique representation of location, and that's to think about grid cells as more like activation of a mini column, and that then there would be unique cells that fire uniquely for each of those grid cells, as shown here. If I had to guess today, I think this is the more likely scenario, the one I'm showing here, and not the one with the multiple grid cell modules. And I can give some reasons why I think that's the case. But the important thing is you have to have a unique location.
And a quick question about the model of objects. We wouldn't need to learn associations or transitions between multiple consecutive layer 4 representations in this case, right? Because we're making association with layer 6.
Right. Which is a great point, Rami. You don't need that. If I'm moving my fingertip randomly over an object or different directions, then layer 4 can't learn any transitions. However, the layer 4 cells are still the same layer 4 cells, and those axons still go horizontally. So in this picture, they're still there, right? And the point about this is that this system can flow between sensory motor inference and learning and sequence inference and learning. For example, if I moved my finger the same way every time when I picked up an object, I learned to say, oh, I'm going to run my, I play with this object the same way all the time. I could pick up my pen and I play with it in the same way. Then the sequence in layer 4 would be a high order sequence because I would be going through the same motion every time. And therefore, I could learn it as a high order sequence. It would be both a sensory motor sequence and a high order sequence. And I see evidence of this all the time, that when we practice something, we go from being totally reliant on, thinking about how we're going to move our fingers and doing it, to basically being able to just play out a sequence naturally as a sequence. Even imagine this is now like a layer 5 column, layer 5, which is the motor output of a column. If I practice the same motor output over and over again, it'll naturally learn to play that as a sequence as opposed to individual sensory movements. You know what I'm saying? You can go back and forth between these two representations. So they're not mutually exclusive.
And maybe another example. Oh.
Sorry, I was just going to say, I'm wondering if we could generalize basically the same system that we're using for models of object, but we use it for models of sequences by just having a 1D grid cell in layer 6A and learning the transitions between basically like going from 1 to 2 to 3 to 4. And if we're building associations with the features in layer 4, then that could drive the sequence learning in layer 4.
I didn't follow that in the beginning.
So if we assume that we have like a 1D grid cell in layer 6A, and we're just learning a sequence, we're not learning a model of objects, and we're building associations between layer 4 and layer 6A, I'm wondering if we could learn the sequence by just having those associations, and we just learn the transitions in the grid cells, like between location 1 to location 2 to location 3, and that drives the activations in layer 4. Because
I don't think you can learn. Can you learn the sequences in layer 6?
Basically, you want to add the
I guess that would be
6.
advantageous if there was something about the movement through the space. Like, I think one example I think we talked about is how, like with songs, kind of like you're saying, Jeff, like L4, you would just learn note to note kind of in layer 4, but maybe displacements through tonal space or something is movement in L6. But I guess, what you're saying, Robbie, is more like, I don't know, just the movement forward in the sequence, whether that's time or action or something like that, is kind of.
Well, you don't know in the layer 6, you don't always know it's going to go in the same direction. I mean,
unless it's a sequence of time, like.
But the sequence, any kind of sequence we learn down there has to be of the sparse representations. It has to be of the population.
But I mean, I assume with Hebbian learning, we're going to like just basically two representations in layer 6A that always happen.
Well, it would be the blue dots we're talking about here, right?
Yeah. So, it'll be similar to layer 4. They would still form associations because we still go from one representation to the next even in locations. It would be just like location 1 to 2 to 3. It's unique to the sequence. It would still form those transitions.
Well, maybe it confused me by talking about 1D grid cells. If I just look at the picture I have in front of me, and I follow a particular sequence of patterns, like I move my finger in the same way over and over again, then that you could argue in theory, then you could learn the sequence in layer 6A. In the same way we learn in layer 4. Is that what you're saying?
Yeah.
Yeah. That could be the one slight hesitation I have on that. It goes back to some of those Thompson papers, and I don't want to rely too much on her work, but it's all I got. So, she just, when you talk about the connections in layer 4, people always say, oh yeah, all the cells send horizontal axons to all the other cells. So this is the horizontal green thing is there. It's very, very clear. But when you look at layer 6A cells, she often describes these cells as very sort of, the axon branches are very sort of vertical. They don't seem to, she doesn't draw them as like they're sending these horizontal axons throughout layer 6A. So I don't know if that's true or not. But that's the only reason I didn't draw that arrow there. I haven't seen someone say, yes, in layer 6A, we see all the cells send horizontal actions across all the other cells. If I'd seen those words, I would have drawn the horizontal green arrow in layer 6A too. It doesn't mean it's not like that. I just don't know.
That's interesting. Yeah.
Yeah. Yeah. It's just unknown to me. There's a lot that's not shown here. It's not shown how grid cells come about here. And for that, there's this need, as I've talked about in the past, there seems to be a need for these one-dimensional sets of cells that fire at different phases. Remember that? The different frequency of the speed. So there's a lot more stuff that has to exist for these grid cells to exist. And that other thing is a bit like if you recall, we debated about, I drew it as a set of cells in the minicom, each one firing at the same rate, but at different phases. And then there was a separate argument made in the literature that it could be different dendrite branches could be firing at different phases. So a lot of mystery here that I don't know the answer to.
I was recently reading or watching some talks on how insects like bees perform path integration, and I've been meaning to share my notes on that, but I think that could be interesting as well, because they have a fairly primitive form of path integration, but it still kind of does the job. And it's also, I think, neurally simpler to implement than full-on grid cells.
You want to make sure it's as powerful, right?
Yeah, but whether it's powerful enough, I guess, is the question.
Yeah, right.
But yeah, so I'll share that soon. But it was interesting how they find a solution to, like, if I found some interesting flowers here or whatever, how can I follow a path from an arbitrary starting location and things back to it?
One of the general themes that we've talked about, and I've observed, is that you think some of these mechanisms start out for very specific problems that animals have to solve, and they're not very general solutions. And then over evolutionary time, what happens, especially in mammals and especially in humans, you've taken these sort of specific solutions, navigating in environments or going from flower to flower, or whatever it is, and we made a very generic version of the same mechanisms, which are now much more powerful. We can use to model anything. So I'm always gravitating towards sort of mechanisms that are very generic, and you have to be careful when studying something like an insect. You might have a solution that works really well for certain things the insect does, but they wouldn't work for modeling, coffee cups with, with logos on them and things like that. So that's just like, I always, when I look at simpler non-mammals, I always keep that in the back of my head. Like, okay, could work great for this ant, but what about, or this bee?
I think it's always just appealed to me because that works in these absolutely tiny brains. And so whereas, entorhinal cortex is a decent chunk of brain. And so, just getting something that will fit inside of a column, I just always thought is an interesting problem. But but I agree with your
we just don't want to get fooled into thinking like, our brains do it the same way that bees do it or something like that. Anyway, this picture I've shown here is from an abstract theoretical point of view, it's very broad. It can be applied to anything, really. This is just about forming representations and forming unique representations, and this mechanism solves sequences and sensory motor, high order sequences and sensory motor sequences, and it can go back and forth between them. So that's some of its appeal to me.
Yeah, I like the elegance and simplicity of it and how it kind of brings back the HTM mechanism into the picture. I guess, yeah, I'm just trying to think through like concretely using it for object behaviors now. And I think the main reason I drew in the diagrams I made, I drew the kind of location as sequence as a separate representation versus stored in the associations in layer 4 was because I don't know, I just started thinking about it right now. So maybe if I think about it for a few more minutes, I'll figure it out. But the issue I see with this is like, how does the sequence work in combination with the location representation? So I have a unique representation in layer 4 for that location at that point in the sequence. But then I move my sensor to somewhere else on the object. So layer 6A representation changes. But whatever feature I predict in layer 4 at that location depends on which state in the behavior I'm in. And so if I don't have a separate representation of the behavioral state, currently I don't see how that works.
All right, so let me just see if I can rephrase your statement. This is if we want to bring in behaviors, which are another type of sequence, behavioral models, right? And so how does that lay on top of this? And
like a sequence of states of an object, basically. Like
well, on the surface, it's not clear to me why it wouldn't fit onto this, but I haven't walked through it yet.
Yeah, I mean, it feels like it requires hierarchy in the setup because I think the object level state, I don't know if this works, but yeah, the object level state would be the input to layer 4.
Well, can I make the
something like
other
that
argument? If layer 6A is a direct implementation of location, well, now we're talking about location and space-time, right? 4 dimensions. And so if layer 6A could include time, then layer 4 doesn't have to change. You know, you could add to layer 4, but it seems to me like, I don't know, it seems to me like given I'm calling layer 6A location, then it's a location in space-time. So
so is that what you're suggesting, that the time is actually encoded in layer 6A and not?
I wasn't, first of all, time in terms of just like how much time between elements in a melody. That's how that was
like the sequential.
We're talking about something different here. We're talking about where we are in a behavioral sequence, right?
Yeah.
I hadn't thought about that, or I can't remember what I thought about it right at the moment. I mean, it's like, oh, what did we think about that? I'm trying to recall. So I don't have I didn't walk in with like a preconceived notion right now saying, oh yeah, that's how we're going to handle that. I didn't. I'm just thinking right now in this mechanism, where would it be? How would I know where I am in this sequence?
When is there a reason we'd want to treat songs and behaviors differently? Like it would be nice if it's kind of the same.
Yeah, so that's why I kind of drew the sequence representation as a separate thing. Like it wouldn't be like a 4D space in layer 6A. It would be, I think I put it in layer 5B, but it could also be like a separate representation in layer 4 or even layer 3, since that sends up the apical dendrites to layer 1. But it would even be a very simple representation. It would just be this kind of one-dimensional next step kind of representation that's always the same if we're at the same location in the sequence of a particular behavior. And then if I'm at that location in the sequence of that behavior, that tells me for all of the locations in that object's reference frame which features to expect.
Right. Well, if I'm following you, there's 2 approaches to do this. One is you start with this diagram at the bottom of this figure, and you say, oh, I'm going to make sure layer 6A is actually representing space-time, and therefore the representation in layer 6A is unique to both the location the object and where I am in the sequence of the behavior. The other approach is to have an external signal, which is sort of a sequence signal of the entire behavior. And then that was an additional factor to incorporate to make a prediction. Does that make sense? Those two basic ideas.
Except for the external part. What?
Well, I mean,
Do you mean
it's
external to the column or to L6?
I'm just saying it's not here in this picture.
Oh,
I
yeah.
I didn't show
So
it.
basically just
Right.
some place that disentangles the current state from the current feature on the object or the current location on the object.
Mm.
Yeah,
No.
it feels a little like how, like in the same way that we have like a local feature and then we have the object ID, it feels like there's a similar thing for kind of the input in L4, like the sequence that might be playing out there versus the state of the sort of what the column is representing, which is the more
Yeah.
central global one.
Yeah, like state is almost like a sub ID of the object or something like that. Like,
But state would have to go through a sequence.
yeah.
But that
Yeah, right.
sequence could be kind of semi-independent, I guess, of what's happening in L4.
Oh, actually, do you remember when we talked about like behavior models and morphology models being in the same column?
Yeah.
We put the behavior models in layer 3 because layer 3 forms these apical dendrites to layer 1.
Right.
So maybe layer 3 could be learning the sequence
Oh.
of states, and each state is a pooling over the activations in layer 4, kind of like the object ID, and then we might have a pooling over states for the global object ID.
That's interesting. Yeah. It's an interesting idea.
And then layer 3 could still be using the kind of associative mechanism that you drew on layer 4 right now for predicting the next element in the sequence, like the next state representing SDR.
Well,
Yeah, or layer 5, because I mean that also has apical dendrites in L1.
The theorist in me would like the following to occur. I would like the representations in these two layers, the layer 4 and layer 6A, to be unique to both the object, the location, and the where you are in the state of the behavior. That would be the cleanest way, you know.
Yeah, I think it would be in that example.
So the question is, if it was layer 3, if it was layer 3 was representing the behavioral sequence, that is what you're suggesting, right?
Yeah, so basically you could think of it as like the SDRs in layer 4 are unique to the location, object, and state. But then we pool over those in layer 3. We pool over all the SDRs in layer 4 that correspond to the same state of the same object. And that's the object state representation. And then we can learn a sequence of object state representations that is conditioned on time coming from layer 1.
I got that. The question then I had was how do I get layer 6A to be unique to state as well?
Yeah, it would have to connect to the layer 3 state representation, basically.
Yeah, I don't know if it
conditioned on
does.
that.
It might. I don't know. I don't know if it does.
I mean, it connects to layer 5 a lot. I'm still unclear why it needs to be layer 3, but I don't think that matters too much.
You're saying maybe layer 5 is that state?
Yeah, so in the original diagrams I made, I put it into layer 5B and used those apical dendrites. I just thought back at because I just read the document we wrote back then where we put the behavior model into layer 3, so thought that could be an option too, but yeah, either one, I think.
Yeah, I like this idea. I mean, if I'm trying to summarize it in a way that makes sense to me. It's like you have, all right, let me see if I rephrase your proposal. There's another set of cells that represents the behavioral state. I imagine it would be unique to the object and the point in the state space, where you are in that, right? And then I assume it's unique to the object, or it's unique to the behavior, maybe. I don't know. I don't think about it. But anyway, and so now you have
Isn't the idea with behaviors that they are objects? Because we have columns that are dedicated to behaviors.
Oh, was Vivian's? I thought she just abandoned that.
No, I didn't. It would be like the state SDR would be unique to the object / behavior model, depending on what the column is getting as input.
Okay, so we have a column that's just modeling behaviors.
Yeah.
Is what we're talking about now.
Yeah.
And so layer 4 is representing changes, changing features.
Yeah.
Layer 6A is representing where in space those changing features are occurring. And the other cell is saying, where are we in the sequence of these changing?
Right. Yeah.
Well, it's an interesting idea. I guess it feels like it needs a little flushing out. It's like one of these ideas, like you think about it and you go, oh, and then you think about it some more and you go, oh, wait a second, some problems with it or something like that. Maybe it just feels early. It's just a little bit too simple, too early, not too simple.
I think it would be helpful to think through like a sequence that's being represented in layer 4 versus a sequence that's happening in whatever, layer 5 behavioral state, whatever. Because with that separation out, it's not clear why you need any sequence memory in layer 4.
I feel like this is how in my mind, this was how we thought about it before, and that's how I showed it. Like,
yeah, no, I agree.
And everything.
I think it is how we've been talking about it, but so now we're trying to bring back in sequence memory in layer 4.
Yeah.
And so the question is, how do they fit together? Do we need both? Like, that's what's not clear to me.
So I'm not sure why you're saying bring back in sequence memory in layer 4. Because these are behavioral.
Because we've not really been talking about that. Because yeah, I agree with you, Vivian. When we've been talking about behavioral sequences and stuff, it's been kind of at the object level, and so we've been saying kind of, okay, this is the state we're in, and so if we go to this location in our reference frame, we're going to predict a particular moving feature or whatever.
Yeah.
It's quite different from the HTM sequence memory.
But like, why couldn't we have the same mechanism in a different layer, like layer 3 or layer 5? Especially since, as far as I remember, layer 4 doesn't really have apical dendrites to layer 1.
Well, just a complication of that. That's been the classic view because stellate cells do not have them. But now more and more people find pyramidal cells in layer 4. So there are some cells in layer 4 that get input from layer 1.
Okay.
But not most of them. For what it's worth. So I didn't follow your conversation a second ago. I'd like to. So maybe you can try just saying it again, and let me see if I understand it. This is about why you're arguing about why we might or might not need sequence memory in layer 4.
Well, I guess for the past few months we've been talking about behaviors and kind of time and all this stuff. You have like a different kind of state of the object or the behavior. So like stapler is opening, and so now it's in this kind of more open state, and so that's where we kind of learned in this behavioral model kind of some moving features at a particular location. And that's where it kind of, like you say, it's sort of a space-time model, because it's kind of like location in the reference frame and the point in the sequence determines what kind of features we predict. And that was always at kind of a global, like object level kind of, okay, this model is now in this particular state, and that's what's conditioning our prediction. Whereas sequences in kind of classical HTM are more kind of low level sequences. It's like the node A, then B, then D, or whatever. And so that's why it feels to me like if we're going to have both, maybe it's something about hierarchy where it's kind of like the output of a lower level learning module would be kind of low level in the receiving one, but and I think this is kind of what you're arguing, Vivian, like maybe we don't need sequence memory in layer 4. But I think, and that's why I think it would be helpful, like what is an example of a behavior where we want both, where we want the low level sequence and where we want it at the global level.
I'm not sure what you mean by low level sequence. That's confusing me a bit.
No, sorry.
Well, I think it's like whether we learn a sequence of input features that come into layer 4, or whether we learn a sequence of states of the entire object. That's like the object ID is represented in layer 2, 3, and that object goes, or that behavior goes through a sequence of states, and those states influence all of the features and locations on that object.
Yeah. Let me just throw out an idea, maybe it'll help, because the way I would prefer this to look, again, elegance often is worth something, but sometimes it's wrong. That if I have 3 layers of cells for whatever reason, maybe the 3rd layer is representing the behavioral sequence, I would love them to all work exactly the same way. They all have many columns, they all form these sparse representations. They can associate with each other via the vertical blue-green arrow, but they would also all have the ability to learn patterns within their own layer, as in the horizontal green arrow. It's like it's available if it's useful. It's not, if it's not useful, it's not learned. So to me, I never see a harm in having these horizontal connections, which are pretty much a prevalent feature for most layers. The one exception being, I was just talking about maybe in layer 6A, but it's a pretty prevalent feature in layer 3 and layer 4 and everywhere. You get these horizontal connections. So that to me, if every layer of cells has this basic architecture, then every layer of cells has the ability to learn high order sequences of whatever it's representing. And if it can't, it can't. If it can, it's useful. So that's not addressing specifically the question you were talking about, which I'm still confused about. But
I think that means, yeah, there isn't really an issue with doing both, with allowing layer 4 to learn sequences, but also being able to learn sequences of object states in a different layer, disentangled from it. Right?
I think again, I'm not really following your and Neil's argument, but the general idea is there's no harm in having it there, and you can ask under what conditions would these horizontal connections be useful.
Yeah, and then I guess then it's also kind of a question of, in general, we've been talking about how time is obviously helpful or maybe critical kind of for a lot of these sequences. And so then it's also kind of like, does that mean both layer 4 and whatever layer is representing kind of object level state is getting time input?
Yeah, I don't know. Interesting question.
Maybe, I don't know if it'd be a helpful exercise to try and think about how would we represent a song if state is kind of at the global level. Because
is state a global level thing? I guess it's certainly.
Well, again, that's how we've often talked about it. It's like,
couldn't it just be a voted on layer?
Yeah, I mean, if we have a song, we could just learn it in layer 4, and maybe it is kind of how Jeff says, that every layer has the ability to learn sequences, and if it's sufficient to learn a sequence in layer 4, then maybe those neurons form more dendrites to layer 1 to get the timing. But then if it is a sequence of object or behavioral states that require more pooling over multiple locations, then we would learn it in a different layer as a sequence there.
Yeah, because I'm just worried if we're kind of not understanding it clearly enough or something, because it feels kind of messy that it's like both of these are kind of learning, and it's not super clear to me why it would happen sometimes in one layer and not sometimes in others.
Mm. I'm not following everything you guys are thinking about, but again, if it may be helpful, just continuing on with the thought I had earlier. Imagine you have multiple layers, 2, 3, whatever. They all work on the same mechanisms. The differences between them, so they all have these horizontal connections. They all can form, they potentially can form the associative connections between them, like the vertical green arrow. And some may or may not have time. So, but they're updated by different things. Like in this diagram I have here, one's updated by sensory features and the other's updated by movement vectors. So they're all the same. They have different things update them. And maybe some of them can use time and some can't use time. That doesn't violate the basic principle that I'm trying to achieve here. And then you could say then you could look and say, well, what if I had 3 layers of cells and layer 3 gets time and layer 4 doesn't, and layer 6, I don't think it does, but you don't know. But anyway, my point is the idea that you have these multiple representations, each layer has a representation, each one is trying to, predict the next input, and each one is driven by some different driving force, and they all settle together. That's a very powerful idea. So I just don't understand what you guys are. So I'm just saying time does not have to be necessary for all these things to work under the same mechanisms. It doesn't necessarily require that all the layers have time. It requires some of them have time, but not all of them.
I think this is going back to like one of the earliest ways that we thought about behavior, which was that layer 4 gets the features, layer 6 gets movement, and like layer 3 gets the changes. Those are like the driving forces.
Right.
Yeah, I think I copied a slide to the Zoom chat, or I posted a screenshot to Zoom chat where if kind of all the layers work as a mechanism, there's no reason why the behavior model cannot be in like a child LM, like there, and then so basically we thought of
Shall we go look at this diagram? Are you showing a picture?
Sure. Yeah, it was like
I'll stop sharing then.
Oh, okay.
You said you posted an image. I didn't know if you were talking about that Zoom.
Yeah. On the Zoom chat. Okay, everybody opens. It's like a slide.
How do I get it to be big here?
Could you just share your screen, Jose?
Yeah, sure.
That's a good idea.
Yeah. There we go.
Yeah, that's good.
Yeah. So I think that idea of a feature going to layer 4 and then changes going to layer 3 was our
I'm
first
sorry,
idea.
what are we looking at on this image now right now, Jay? What do
This compositional plus behavior model.
Okay.
Where at some point there was an argument for the behavior model cannot be like in the child LM, but must be on the parent LM.
I think that was just about when we apply a behavior to a morphology model that we could use that connection, but the child LM could still have learned.
Behavior model.
Yeah, but then I think that's when we put both models in the same column still.
Right.
Okay.
Right, but I'm not sure. That might still, that's where our current leanings, we're having them in different columns, but if you want to make an argument why, but I'm open to discussion about alternate flavors.
I mean, I guess I personally like things going the features going to layer 4 and changes going to layer 3, which means that like the behavior model, morphology model can exist in the same column. I think the reason why we separated it out was because we didn't want to keep track of 2 different reference frames for the behavior model and the morphology model.
Right. That was one of the big reasons.
Yeah.
And because there wasn't really a reason to keep it in the same reference frame, in the same column. So like even if we send the changes to layer 3, that still doesn't solve the problem like that we have right now, which is that yeah, even like just because I'm detecting a change at one location right now, and I know which change to expect next at that location, if I don't have a separate state variable, then I don't know what change to expect after I move my sensor somewhere else.
Yeah.
I'm sorry, but Vivian, my recollection was part of what Jose said is that one of the real things that's pushed me over the dark side of having two different, a behavioral column and a non-behavioral column was because it required two separate reference frames, and that seems almost impossible. Jose, are you suggesting there's a way of solving this with one reference frame?
No, I'm just wondering like where we're kind of converging to, because I feel like we kind of started with one and then went to another and then kind of coming back to the first one.
Well,
I think we're still saying one because we're still talking about
Okay.
behavior models.
Yeah.
We're not talking about morphology right now.
Yeah, we're
Um,
just talking about having different states in a behavior model,
Okay.
independent of the morphology model.
So we still have two different columns, one that contains a morphology model and the other that contains a behavior model. And we still don't know how to exactly kind of use that behavior model to predict the features for the next step in the morphology.
were you saying we don't know how to have those two models interact, the behavioral model and the morphology model?
It sounds like it's still an open question, but maybe I'm wrong.
Yeah, I don't know if we.
I mean,
Yeah, but
we've talked about that,
unrelated.
but that's I guess a different topic from what
Okay.
we're discussing
Yeah.
today.
Okay.
Well, I mean, although I've embraced Vivian's suggestion of having separate behavioral columns, there's
Yeah, I
something
don't see why it's the dark side. I feel like it's much more elegant. It's
I know,
like
I know.
the exact same mechanism.
But now
We
we're basically divided columns. The whole cortex has got two types of columns, and
It's got
Many
many
types of
types of columns.
I know. I understand
They're all
the
columns
argument.
still.
I just
Yeah, they're all
feel
columns. They just get different inputs.
all right, I'll just state it. I've accepted your logic, but there's something that still slightly bothers me about it. So I'm not like, oh yeah, that's it. It's like, okay, it seems to work. Yeah, it's pretty good. There's something irking about it. So it's okay to think about, I don't want to revisit it completely, but if we stumble upon something which makes us question that, then I don't mind pursuing that a little bit. Yeah.
Can I what you call it? Yeah, just on what we were discussing earlier. I don't have a great drawing or whatever. I've got some things to point at, but can I try and kind of just get a little bit what maybe the open question feels like?
Sure.
If I share my screen.
I'm confused by that. Oh, great. Thank you. This clears it up right away.
Right. So basically, we've been talking about different kinds of sequences, behaviors. We've been talking about things, as you describe often, Jeff, as like a higher order sequence. It could be a song, it could, a sequence of letters, whatever. And we also talk about things like staplers opening and closing. And if for the moment let me get rid of this. For the moment, yeah, you just kind of see this one on the right. In general, so this is a kind of behavior or sequence modeling column. So if we say it's learning songs, and if we say it's learning through HTM, then we would say that it's getting, A and then B, and these are coming into layer 4, and then it's what you call it? Yeah, then learning this kind of transition structure, which may or may not be conditioned on time. And then if it's more like something like a stapler, then that's where we talked about, okay, the input feature is actually a changing thing learned at a location. And so that's where, we would learn a bunch of kind of local flow patterns here, and then a bunch of local flow patterns here. And those local flow patterns over here are associated with a different global state or kind of state for the entire object. And with the conditioning of like,
The entire behavioral object.
Yeah, the behavioral object. Yeah, sorry, not stapler. So this is a behavioral object. This is the lever kind of behavior, or the hinge behavior, sorry. Um, that's going to tell us kind of based on where we are in the hinge behavior sequence, which is some kind of more global thing, and where we are in the reference frame, we can know what we should predict, like some flow patterns here, or in a different location in the sequence, some flow patterns here.
Where's the information where we are in the sequence?
So, I mean, I guess we've discussed different locations of that in the past. I think, yeah, both layer 3 or 2 and 5 have come up as candidates. I guess the advantage of 3 is it maybe makes it easier to communicate to higher levels.
Well, layer 5 projects as well.
Okay. But I mean, it's always felt to me like layer 5 would be nice just because that's the kind of motor output. And so the connection between kind of behavior and action is so close that, yeah, but anyway, so I think that's like the starting point for, I think, what Vivian and I were talking about, which was just like, or at least what I was trying to say was, okay, today we were now talking about HTM, and it's kind of a different kind of sequence, almost like a different kind of behavior. It's still time conditioned and all this stuff. And so then the question is it really something different? Is it like you're saying, like maybe kind of sequence learning is happening in kind of multiple layers, and it's a case of whichever ones have kind of associative connections and maybe have access to time, they can do it. But I guess what I was just thinking, what I was trying to say was that if you imagine there is a global state, but we don't actually represent the transitions between states here, instead you feed the kind of hypothesized state up, then that becomes a bit more like an input, like A or B or whatever. If this higher level column is then actually keeping track of the sequence, then it could condition the lower level one and say, oh, you are in this state, or now you're in this state. And so then this behavioral model.
But why did you dismiss the idea that it could be learned locally in the first column, the sequence?
It just feels like, it feels a little bit like everything, like having multiple reference frames. The idea that or like, I don't know, it just feels kind of weird to me that it's like, okay, songs are learned in a totally different way from staplers opening and closing. And
It would still
maybe
be
they
the
are.
same. I mean, it would be the exact same mechanism. It would be the HTM mechanism, just applied to a different layer.
But that's what I mean by different. It just feels a bit weird that it's learned in a different layer.
But
and it wouldn't be a different reference frame. It would just be a sequence.
So again, going back to the argument I made earlier, I think every layer in theory could learn sequences if it made sense for them. So it's not like I'm representing it. It's this inherent property of a bunch of cells. So it's not like I'm doing extra ones or a second place or something like that. Whatever it's representing, if it can learn sequences, it'll learn sequences. So I don't know. I guess I'm not ready to jump into the hierarchy yet until I understand why it doesn't work in R1.
Well, just for example, okay, so now we need multiple layers to have access to time. But we've also talked about how for time to make sense, it needs to receive feedback from the columns to basically tell the matrix cells whether to speed up or slow down. So now we also need multiple layers projecting to the matrix cells to tell them whether to speed up or slow down. It just feels like it brings complications by having every layer kind of be able to do this.
Maybe not. I mean, it's not clear that's true. You know, all these layers are connected together, so it would be sufficient as an ensemble of layers that they tell the matrix cells what to do. Not every, as long as there can be somebody who can represent the group correctly, then
yeah.
And by the way, learning sequences doesn't always mean you have to learn the timing of the elements.
Sure.
You know,
but at least we know they are kind of things like this that we want to have time for, and there's things like this that we want to have time for.
It's funny because when you show those two pictures, my first reaction is want to make them the same. I want to see why A, B, D, F, A is the same as stapler opening and closing. They're like,
that's kind of what I'm trying to get at with the hierarchy. Is it just feels like if this state is passed to this one, and that's what's conditioning, or that's the one that's keeping track, then the actual kind of sequence is just being learned here.
well, I don't know. I guess to me, the hierarchy, we found one reason for hierarchy so far, one good reason, and that's compositional structure. And so if we want to view this sequence memory as somehow compositional structure, I'd be more happy to talk about it that way. But it's not clear to me we're talking about that. I'm still confused, but
I mean, maybe that is one way to, because in the sense that this is a song is a higher order sequence of very simple objects. It's direct sensory inputs, it's notes. Whereas
well, it
stapler opening and closing is a sequence of a morphological object. So it seems like it makes sense that the input in some has to be an entire object and cannot be or in this case hinge behavior, sorry, it has to be kind of a representation of it of many different changes going on at once. And so in order to represent a behavior as complex as a stapler,
that could be,
it has to be compositional.
You could argue that's a difference in quantity, or you can argue, as you're saying, it's a difference in quality. I'd rather shoot for the difference in quantity, like, okay, one's one-dimensional, one's two-dimensional, or something like that. And what's it, grid cells represent one-dimensional objects, and they represent two-dimensional objects, the same grid cells. So why couldn't I do the same thing in a single column? You have, it could be representing one-dimensional sequences and two-dimensional sequences. And I guess I'm always hesitant to jump the hierarchy until I'm absolutely proven that.
Yeah, no, I know it also has.
The nice thing about hierarchy is I could say I need two columns because the columns are representing two different objects. That's what they're doing. They're representing two different objects, and I'm trying to find the relationship between them. That I'm willing to hang my hat on. Old expression. That it means
Niels, do we lose the location by location basis of changes if we just pull over object states like this? Because what you're describing sounds like second order pooling, so we pull from features into an object state, and then from object state into an object behavior. And I think we discussed this in the first retreat, but we ended up saying that we want those changes to be at a location by location basis.
Yeah, I'm not sure. I guess I need to think about it. But I mean, the location by location basis, that's captured more in the top-down connections.
Yeah, I think it would work with Neil's proposal that like if R2 would learn the sequence of states, it could inform R1 which state to expect, and R1 still has a model of which locations to expect, which feature set for each of the states. But it's a lot of machinery required for a very simple task of learning a sequence.
Right.
So, and I agree with you, Jeff. Like if this is the hinge behavior, then what is this? Are they? Yeah.
Right.
So
right.
I'm not proposing this because I think it's perfect. It's just when we were talking about it being in this is basically me thinking out loud about, okay, it feels weird that songs and staplers are different. I want to try them to understand them in a more similar way. This is just one of my intuitions for how to do that.
I didn't follow how you got to that. Right. In my head, I'm going to reserve hierarchy for when two learning modules are representing two different objects. And we're trying to, that could be two different behavioral objects. I'm fine with that. It could be two different physical morphology objects. I'm fine with that. But they got to be two different objects. I can't use the hierarchy as a convenience of like, oh, we need to put something and stick it over there. That doesn't work for me. It's like that's the lure of the death of hierarchical solutions. So I don't like that. It's not clear to me.
Siren of hierarchy.
You're ahead of me on this news. I'm not keeping up with you. So, but I'm not yet. It's not yet clear to me what the problems are we have doing this with one learning module. You've jumped ahead of me, and you can see.
I mean, yeah, it's. I agree. It's possible. It's just, I think, as you often say, that like sometimes you just have a feeling that something feels kind of off.
Okay, but I'm not sure it is. I look
all.
at those. I look at sequences in the staple and I go, "Oh, those are really the same thing." And you're telling me they're different things. I'm like, well, I'm not sure why they're different things. They seem like they could be the same thing, or I certainly would like them to be the same thing. Why would I, make a distinction between them? I don't know. That's a tough one.
So I guess, yeah, if we maybe for the time being embrace the idea then that, okay, layer 4 and layer 3 or 5, wherever the state is represented, and maybe any layer can just learn sequences if we have repeated transitions, then they will kind of learn that through associative connections, just HTM.
It's natural. There's nothing has to be done.
And then it can also be time conditioned.
Right.
Then
where do we end up on the idea that I'm sorry, my memory is really, really bad. We were talking about layer 6A as potentially being 4-dimensional space-time or just 3-dimensional space. Did we come to
I would argue for it just being 3-dimensional space, because that's what we need to path integrate through, and then having separate representation for a sequence, because there we don't need to be able to move through it arbitrarily.
Well, there's the last sentence didn't make sense to me, but
like in the sequence we only move from the current element to the next element to the next to the next. In 3D space, we have to be able to move through it arbitrarily.
Right. Well, we do that with the movement vector, right? That's grid cells. But why couldn't, in the grid cell literature, there's a lot of evidence that grid cells represent episodic time, sequences of time. There's people, your episodic memories are sequences of things. And so my first reaction would say, well, can I get grid cells to represent space and time? And why is that hard? I mean, yes, I need to path integrate through space-time. Well, I can path integrate using movement connectors. That's the hard part, but we know it works. So now I have to do is add another sort of quote movement vector, which is just time, and I can't, and that's something I can't control. It just moves ahead on its own, but it's another type of movement. So I can have, is it possible? It's not clear to me that grid cells couldn't path integrate through space-time. That they would.
Yeah, I guess you could represent it as a 4th dimension, but movement along the 4th dimension would be very different from movement.
It would be. It would be. It's just the thing that drives it would be different, right? But I don't know. Again, I'll go back to the literature on grid cells suggests that they represent time sequences as well as, other things. It just seems to be very, very flexible about what they represent are episodic memories. And episodic memories are often time sequences of things, right? Almost always there. So I would think the evidence suggests that at least grid cells in the entorhinal cortex are space-time. And then at least then for me, from my perspective, it warrants thinking about it a little bit like, oh, what would the mechanism be if I had to add time as another path integrating factor?
Yeah, I mean, maybe just to kind of carry this discussion forward, nothing concrete, but we often talk about kind of examples of things where it is easy to sort of path integrate through a sequence or kind of a behavior, and instances where it's not. So like things like songs or rhymes or whatever, like the alphabet, A, B, C, D, it's very easy to go in one direction, but it's very hard to go in the other direction.
Right. That would be like the time movement is only in one direction, where physical movement of the sensor can be backwards and forwards. And, you know.
Yeah. Yeah, we could represent it. We could have it learned in layer
Just
6.
think of time as
But then,
movement.
but sorry, but so if time, if we can't sort of path integrate or go back through time in the representation, what is the advantage of having that as part of the sort of path
Well, we
integratable
need to we need a way of if I'm trying to get to layer 6A representing space-time. That would be the simplest solution for me. Because then when it projects to layer 4, it says, here's what I predict at this point in space-time, as opposed to this point in space, and then layer 4 has to integrate time from someplace else. So very simply would say, if a layer 6 can incorporate space-time, 4 dimensions, then layer 4 works just as it does today. I don't have to do anything differently.
It just feels kind of like we're already struggling to fit grid cell or like a path integrating cell into a column, and now it also has to represent time. Whereas it feels like we have a straightforward neurological basis for the, like if state is just conditioning apical dendrites,
well, you know,
then it's just like another input.
After our last research meeting, I tried to come up with mechanisms. I spent a day and a half on this, trying to come up with the actual neural mechanisms that would allow neurons to make different predictions under different times and different contexts. And I couldn't solve the problem. It was just got really, I just couldn't come up with an answer. It doesn't mean there isn't an answer. I couldn't come up with it at that time. I was like,
what's
it
wrong
sounds
with
simple.
just like apical conditioning?
It does sound, I know, it sounds simple. And then I tried to work out the details and I couldn't get it to work. So maybe I just was having a bad day, or, you know.
What was the issue that came up?
I'm trying, I know I was afraid you were going to ask me that. I don't remember. I was deep into it, right? I'm taking notes. I'm just thinking and scribbling notes and stuff. I don't know. I have to go back and look at it again, but it just didn't pop out at me. It was like, I don't know. It sounds like it ought to be simple, but you know, I was trying to figure out, oh, I have these calcium spikes, and I have these back calcium spikes, and I have these, what could the neuron, how could the neuron behave different under these different conditions? And how could it make, how could the apical input enable one set of basal dendrite behaviors and another apical input enable a different one? I just couldn't figure out how to make that work. So anyway, I
mean, I feel like it should definitely be possible to do it with like 4D grid cells, but it seems a bit like too much for such a simple thing. Like we could just have unique representations for each state and then use the sequence memory algorithm to associate the current state with the next state.
I got it. But I'm going to go back to the idea that grid cells in the entorhinal cortex seem to do this. We could go back and look at the literature on about them encoding sequences and so on. They just seem to be extremely flexible. They can represent one-dimensional space. They can represent two-dimensional space. We don't know if they can represent three-dimensional space. The verdict is still out on that one. But we do know they represent time and or sequences and episodic memories, which are sequences of events. So I would say, and by the way, it might be possible. It might turn out that when you try to understand how grid cells solve space-time, not just space, it may make them simpler. That the addition of this additional requirement may suggest an answer, which is like, oh, it's much simpler than we thought. It's always a possibility that happens sometimes.
So yeah, I guess one thing that could be nice about it is that, like, we might have sequences for behaviors that aren't just transitioned by time, but are instead they're action conditioned. Like opening the stapler is usually not something that just kind of happens on its own, but you apply an action and that makes it change states. So if we had a general grid cell mechanism, it could kind of learn how actions transition you through state space.
Yeah. Right.
So that means layer 3 is now going to be pulling, like the most general thing would be a behavior ID, but if it's not really moving, then it would be just an object ID. So basically, with 4D grid cells, layer 3 has the ability to pool and just represent behavior ID.
Well, so if I have 4D grid cells, it's possible that layer 4 and layer 3 have no idea about this. They don't know. They're just associated with some SDR coming from layer 6. And they have no idea what that means. So anything beyond that is going to work the same. So the pooling will be the same. It'll be pooling over things that are occurring in 1 dimension, 2 dimensions, 4 dimensions. They don't know.
So it could be a behavior ID or an object ID. If
It would be an ID representing all these patterns, whether they're 3-dimensional space or
very simple.
Or space-time. Right.
Maybe just one thought, kind of tying back to the conversation we were having the other day about sort of a generic reference frame versus, or like a reusable reference frame versus kind of specific predictions. Because
I'm sorry, I don't remember that. What's a reusable?
That was the conversation about like mugs, how you learn kind of many different mugs, and then you might get kind of a reference frame.
Like that. So the idea that classes of objects could be all have the same reference frame.
Yeah.
Or same.
Yeah,
anchor.
but then you'd have kind of the state would help you predict deviations from that.
Right.
And I mean, that feels relevant to this discussion because it's kind of the same thing where it feels like if at least a naive implementation of a 4D grid cell is literally adding an additional dimension. And so you have this explosion in how much you need to represent and learn. Whereas with kind of something more like what we discussed then, over time in different states, a lot of the information you've learned about an object is redundant. You can reuse that. And so the state conditioning just needs to tell you what is different. And that's clear, at least in my head, how that would work with the state being separate rather than kind of adding this 4th dimension to
it's funny. It's funny. I almost jumped to the opposite conclusion.
Okay.
My first thinking is like, oh, how would I add that to layer 6? How do I think about layer 6 in a way that encompasses the different classes of cups? So you might be right, Niels. I don't know, but I was like, oh, well, what does it mean to have this path integrable space thing? I don't know. I just felt like, oh, well, time is one other dimension we could add, and I don't know. I see your point. I see your point.
Yeah, it's a good point. I'd forgotten about that. I think that is a pretty strong argument for it being kind of separate, so we don't have to relearn all the things that stay constant.
Well, why would it force us to relearn something if I didn't do that?
Yeah, not in the behavior models, because there we're only storing changes. But I guess if we have a morphology model that has different states, but these different states might only differ in like small variations, like the open and the closed stapler, if you have a morphology model of both, we don't really need to relearn how the bottom of the stapler looks like.
I know that, right?
I mean, partly it depends on how I guess the space-time grid cells work. But I guess if we at least agree that in Monty with like 3D Cartesian space, and then we add the temporal dimension, and so we're going to kind of we have to replicate all the information that's learned at every new kind of slice of time, then we have a significant increase in the amount of kind of information we're trying to represent and potentially need to learn.
We haven't. But
maybe there's some way that I don't know. Maybe it's only the grid cells that change over time that differ. Or, yeah.
Well, it's possible that you could still have 4D, grid cells and then a separate sort of class representation. I don't know. We still haven't resolved how to learn these behavioral models, because a single column doesn't seem to be able to do that, and it's just doesn't have enough time to learn everything. I mean, it could represent it, but it can't So that was another issue we haven't resolved, is like, well, it clearly takes, you know, a bunch of columns working together to learn this behavioral sequences. We don't know how that's happening either. And that's a hole in the theory, you know, implementation. That may not be a problem for Monty, because Monty can do anything.
Can I
Yeah,
suggest something that complements what Niels was saying?
good.
So back then when we talked about this, I also suggested, so what we're seeing here is basically the location being like a generic location, and then for the different instances of this object, we have like a specific SDR for these locations. But what I also suggested was that this location that basically represents time the same way, where the generic location is not changing, where it's like this location on that object, but the specific would be, as it moves, it's just changing which cells in the mini column. So it's representing time in that way. And then if we assume...
I'm not viewing that's representing time. Wouldn't the pose representation or the orientation representation be changing as well as when that lid goes up? I mean, so wouldn't the square sort of rotate with the
Well, that would be in the features. I'm talking about the location in 6A. So and I'm just saying that maybe, I know that you said, Jeff, that layer 6A doesn't have these connections, that like associations that may represent transitions, but I'm saying...
I said only that
Yeah.
the Thompson paper didn't suggest them, so
But
that doesn't mean anything. It's just one little data point. So I'm not hanging my head on it.
But I'm suggesting that maybe if they exist, then we could learn also connections between states the same way.
Right. I think as a high level comment, I would agree with that. I'm not sure how that relates to the picture of the stapler here, but
it's just that if we were going to say, like, this is basically what Niels was also suggesting, that if we're going to represent 4D grid cells, we could just represent the time axis as a distortion in the location, or like a variability from some generic location. Did I get what you were saying?
Yeah, I think maybe one thing I just need to understand better is because I think in my head that was like the bottom of the stapler would be the same. And then you would need to represent the parts that were changing. But I think when you were describing it, you mentioned that the location on that tip of the stapler that's moving, that location is constant. I'm not saying that's wrong, but I just feel like that's different, and so I just want to...
I thought we broke off the top of the stapler and we're using the existing model for the stapler, just restricting it to the top, in which case there's nothing, it's just the same object, it's just rotating.
Right, this doesn't assume hierarchy. So we're assuming it's one object. So this is why I also had this the balloon thing for the distortion. Basically because we can't break this into multiple objects. But yet still these locations we can represent how they change or distort over time.
And maybe it helps also just to try and use the language of like a behavioral model. So it's like, actually all we're representing here is local flow patterns. There's no concept of a stapler head, at least not in the sort of hinged behavior model.
Yeah.
This to me would be like, you know, an object like this balloon, in some sense, you could argue that it's not changing shape at all. It's just, you're looking at different scales and you're seeing a flow between those scales. I mean, I can see a balloon that's close to me and further away and then further away. And of course it changes in its size, just like this image does. But I don't view them as, I assign the exact same reference frame to them. I just scale it. I just am able to scale the reference frame.
But there are other distorting behaviors where you
I
can
know.
just...
I know that. But I'm saying this particular one, sometimes when we use examples that have a simpler explanation, it's not a good idea. It's better to focus on the ones that are more complex, because that
all discussions lead back to the can of worms.
I was just gonna say that. So we should talk about can of worms.
But yeah, just briefly. Oh, good.
Can of worms is equivalent to a crumpled t-shirt. Yeah. In the behavioral model and the morphology model. Sorry.
I was just going to say on the like 4D topic, I think, at least in my mind, in terms of Monty, like no matter how it would be done in the brain, like whether the fourth dimension is part of the grid cell representation or if it's a separate sequence representation, I think we'll end up with conceptually that the models become four-dimensional. So we have three-dimensional locations in space and then an orthogonal, totally orthogonal fourth dimension of states or time in which we learn these things. And so, yeah, basically in how I was kind of describing it for in Monty would be that we have the usual models, but then all of these like XYZ locations for each feature are conditioned on the state. So it can be different states depending on the state or the element in the sequence. You expect different features at locations or different changes at locations. And then similarly for inference, when we try to infer where we are, those hypotheses would extend in the fourth dimension. So we would have to infer like which state we're in and what location in that state on the object in that state. Yeah, just kind of to highlight that I think like conceptually it's definitely valid to think of it as 4D space, and then the question would be how would it be implemented in the brain?
Well, I'll go back to something I think Neil said earlier, something like that, but somebody did. The layer 6 is highly interconnected with layer 5, and so if layer 5 is representing, like, we think about it as movement, but movement is also behavioral states as well, right? It's in some sense. I'm just saying, I'm going back to trying to get layer 6A to represent 4D locations, and so you'd have the locally there. You'd have your signal there. Layer 5 would be the thing that might help layer 6 represent 4D space. I'm just throwing that out. I think it's worth trying to me, it's worth trying to get layer 6 to represent 4D space. And that could be separate from, states of objects, like classes of objects. A tall cup doesn't become a squat cup, a short cup. That's not a behavior. That's just two different flavors of an object. That could be separate from things that change and morph into each other.
Yeah, or
did we make any progress today?
Yeah, I mean, maybe I misunderstood what you said just now, but like it feels like if we did to be devil's advocate for space-time grid cells, then yeah, a class would just be the grid cells that are active for like the reference frame that's active for the different objects that it could morph into and things like that, because they would share the same space-time space.
Yeah, well,
then,
a devil's advocate, like you're advocating for it, you're advocating against
yeah,
it.
I'm advocating for
that
because
okay.
because I guess earlier
I was the advocate.
That's right.
That's okay, fine.
You're confused.
Heavenly advocate for space-time grid cells. There's that, and then I guess the other thing is just for behaviors that aren't just sequences, for things like the joystick or just the complexity of objects that can kind of go through time or kind of go through their behavioral sequences in different directions, go through behavioral space in different directions.
Right, they're not sequences. That's a very different thing. That's, to me, in my mind, that is not a behavior. That is just, this thing can move in the world. And
But somehow we
know.
can understand and we can model it. So it's
Well,
not.
that's right, but that to me that could be equivalent to like, oh, I can pick up my cup and move it to a different part of the table. I can, there's no, it's not an inherent property of the cup. And so, if I have a joystick and I can move the top in different directions, well, yeah, it's limited, but it's certainly, it doesn't seem like there's some set behavior for it. It's like I have a limited area in places I can put my cup on the table. I have a limited areas I can move this joystick top.
I mean, isn't a stapler just like a one-dimensional version of that, like a more limited one?
Well, because no, but well, the fact that it is limited is the difference, right? The fact
But
that it is a sequence, the fact that it is a high order sequence is the difference. It can be learned as a sequence, whereas the movement of the joystick or the movement of the cup on the table is not. It can't be learned as a sequence.
You can form a sequence from like joystick movement if you just do left, right, left, right. That's
Well, right. You could learn it that way. You might learn while playing a game that you do a certain pattern really quickly. I used to have when I was a kid.
Good.
As a kid, I had this plexiglass cube, which is a three-dimensional maze, and you could see into it. And it was divided into maybe like 10 by 10, so it'd be like 1,000 sort of cubes inside, and had all these. And basically, it was a passage. And you put a ball in one end, and you'd have to try to rotate this cube in all these different dimensions to get the ball out the other end. It was very hard to do because you couldn't really see the passages too well, right? Because it was all plexiglass. And so I learned how to do this blindly. It was like I just learned how to rotate this thing over and over and over again. And it always comes out, and then the fun of it was over. But so why do I bring that up? I don't know. It's like something which started out as a very complex, hard to solve behavioral problem, where it became a high order sequence. I guess that's what I'm bringing up. It became a complex high order sequence. It took 30 seconds to do.
Yeah, it's interesting. I mean, I think that ties in nicely with some things we've talked about before, where even things like a t-shirt, the first time you're folding a t-shirt, you kind of, firstly, you need to learn like a temporary reference frame or representation of the t-shirt in its current state. And then it's a very kind of deliberate sort of model-based thinking of like, okay, how does this thing need to move to a particular location? But then over time, you develop a pattern for like, oh, folding a t-shirt, I grab it by these points, and then I follow this sequence.
Right.
And so I guess what I'm just trying to rephrase is like, maybe there was never really a learned model for the former. Like you kind of leveraged simpler models through a slow process to be able to behave intelligently, but it's very slow, and there's not like a behavioral sequence or something that you can just.
I would agree with that.
grab.
Right.
In
the beginning,
and so maybe the joystick is kind of the same. Like,
right.
it takes a while, and I guess eventually you just learn like a mapping between, oh, okay, if I push up on the joystick, my character moves forward.
Well, that's a step. That way, I don't like the joystick for these reasons. It doesn't to me represent a behavioral sequence. And yet it is a way of using behaviors to affect changes in the world elsewhere, sort of goal-oriented behavior, which I think is a good example for that. But we haven't really tackled that one yet. I'd rather put the joystick into that category. It's a goal-oriented behavior. How do we learn how the joystick controls the world to achieve goals? Which is not a behavior of the joystick. It's how the joystick interacts with other objects.
Like just one more, sorry, like I think we're adding one more thing, but like one more that would simplify, Jeff, like the 4D grid cells kind of model even further is if we represent layer 6A with XYZ, T, and also layer 4 with all the features and also the changes. Because for example, one change that we're trying to extract from sensor modules is like optical flow. So like instead of the changes going into layer 3, they're also going like changes is just another type of feature, if you consider it that way. Then we could just keep the existing layer 4, 6, and whatever model comes out is like a morpho-behavioral model. Like it's not a separate morphology or separate behavior model, but like it just has all of it. And I think that would be like, and even further, like, I'm not saying that that's right, or like we should do it that way, but I'm just saying like, if we're simplifying it further.
OJ, I want to make sure. I mean, I think you were arguing for the sort of the nicety of using 4D grid cells because everything else flows out. Whatever happens, it works. Is that? Or,
Yeah, I mean, I'm kind of.
Is that not what you were saying?
That's not what I'm saying. Well, I guess I kind of went back and forth on whether, like, separating out space and time. Like, at first, I liked that idea because it seemed like it would give us more kind of flexibility in terms of using like one independently from the other, while but now like now I'm kind of like switching back, like, but maybe like representing as XYZ I guess I'm kind of like moving more towards this that idea after this meeting, but and
you're putting a warmest vote on 4-dimensional grid cell. Is that what you're doing?
yeah, I'm just saying that if we have 4-dimension and also include, like change as a feature, then like I'm just like taking that even further in terms of like, okay, let's group like everything together, which might not be the right idea. No.
Yeah, I mean, in my mind,
So I like
the
it. I like
question
ideas.
isn't really whether we have X, Y, Z, T. I feel like we need that, but whether T is represented in the grid cells or somewhere else.
Yeah, I mean the tuple XYZ all together, like in the grid cells.
Yeah.
Yeah. Anyways.
And then just to clear, what was your reason for kind of preferring that, or just feeling
I
like
mean,
that's right?
so let's say that if we are representing grid cells, if the grid cells represents the space time, and so like I'm taking that as a kind of given, and also in layer 4 we're representing features and changes, then with the existing mechanism that we have with the green arrows in layer 4 and the vertical arrows between layer 4 and 6, before with just features and just space we were creating a morphological model, but with if layer 4 can receive features and changes and layer 6 can receive space and time, then those two combinations can create a sort of a combined morpho behavior model.
So you're going back to the idea that we don't have a separate behavioral column. We have behaviors and morphology.
Maybe we don't have a separate morphology and behavior model. Maybe it's just one thing.
But then we can't apply different behaviors to different objects if they're just in the same model.
I haven't thought about that, obviously.
Well,
I know that somebody was going to.
Going back to the figure that Rami showed earlier, at one point we decided the only way when we were still working on the idea of a unified morphology and behavioral models, we reached the conclusion that behaviors can be applied to other models, but it requires hierarchy.
Yeah.
You can't do it in the column.
Yeah.
So the behavioral model in one column could direct morphologies in another column. Now, I'm not saying that's right, but that's how we got to that picture that Rami showed.
Yeah.
Yeah, and for what it's worth, it doesn't feel to me like we need time in the grid cells to have behavior morphological models. Like that's not the blocker. Because I guess it's the blocker if we want to fit it into L4 and L6. So I think to paraphrase what you're saying, I feel like an argument for having time grid cells is that it prevents having to have time represented in another layer. If that's a disadvantage.
Right, you're throwing time into the L6 bucket, and in theory, no one else should know about it. But this is time. This is actually, it's not time as in the matrix cells. Let's be really clear about that. This is sequences. This is time sequences. That's what it represents. It's not timing. It's just
it's more like state space, maybe.
Yeah.
Like discrete states in a sequence.
Right. It's a sequence of states that'll learned in one dimension. Right. I mean, that would be a lovely outcome if somehow if we added time, if we made layer 6 cells, we figure how they represent space and time, and then everybody else doesn't have to change, and somehow we could get the whole single learning module learns both behavioral models and morphology models. I would love that, but I'm not dissing on Vivian's idea.
Yeah, and I still feel like that's a separate question whether a single column can learn both behavior and
But if it came out to
like even if we represent time in layer 5 or whatever layer 3, we can still learn both in one column. Or like in principle, we can learn both in one column. The issue was
if there were problems that made us think about moving to two separate.
I agree, but that's the thing. I feel like those are separate from having somewhere to represent time.
Right. Yeah, maybe I'm going to stop using the word time. It's really representing. I don't know. Again, I want to distinguish it between matrix cells, which represent like timing.
I've been calling it state. Because I feel like that applies more also to morphology models, that you can have different morphological states and different behavioral states.
But in this case, it's states that flow through time and the time the states that change through time.
Yeah, you traverse state space in one direction.
Right.
But but it may also be action condition, as we sometimes talk about. Like it might not be necessarily time that pushes you through it.
Right.
Yeah.
There's always this ordered sequence.
Yeah. It's funny because thinking very theoretically, you might say, oh, objects have different states, or like different classes. And if they transition in a uniform way, we would learn it as a sequence. So there's some sort of potential hope for unifying classes and behaviors. Like classes are the steps along a behavioral sequence, but if you don't have a behavioral, you could still basically you can have different morphology of an object representing different classes, and if they do transition through time, then you'd learn it, and if they don't, then you wouldn't learn it.
Right.
It's an interesting idea. I'm gonna have to write notes after this meeting. There's too many things we talked about.